Okay, let's start. Thank you for waiting, audience. Hi, thank you for everyone. I'm Kinjo from Akindo. I'm founder of Akindo, which organize our WaveHack Global. So today, I'm so excited to able to hold on workshop event with the core team of Mina Protocol for all you guys builders. So also, today's moderator will be Moz from Akindo. Hi, Moz. So can I take over? You, please.
Yeah, thank you for the intro, Kinjo-san. I'm Mose from Akindo and excited to be here for today's session. So let's get started. Let's see. Excuse me. Yeah, this. So first of all, welcome everyone to our WaveHack Global Onboarding Workshop. It's a pleasure to have you with us today, and I'm excited to introduce you to this acceleration program designed to foster the next generation of groundbreaking crypto applications. So let's start with what's WaveHack Global. So WaveHack Global is a prize-funded acceleration program that aims to support builders like you in bringing your innovative products to market with the backing of our top-tier partners. We provide grants and feedback to help enhance your solutions, whether you are launching a new project or expanding an existing project. The program is already underway, and as we gear up for 3 major demo days in Japan this summer, actually one of the demo day, AI+Crypto, has been concluded with huge success. Let's explore why WaveHack Global is an event you don't want to miss. So you have the opportunity to receive grants from leading global projects like Mina, ZKSync, Manta, The Graph, Aptos, XRP Ledger, Zeta Chain, and more. Every 2 weeks, you receive valuable feedback from expert judges of these projects. And our weekly online study sessions will keep you updated on the latest technologies and in-demand products. Additionally, you have the unique chance to pitch at major crypto conferences in Japan, including AI+Crypto, which has already concluded, Aytunc, which will be held at the end of this month, and WebEx for the next month. WaveHack Global is an accelerating program open to all builders, whether teams or individuals, at any time and free of charge. This summer, you have the opportunity to impress a broad audience with your projects tailored to our grant partners, themes, and contribute to the mass adoption of crypto. So today, we are thrilled to have David, Aytunc, and Philip from Mina Protocol leading this workshop. Mina is the world's lightest blockchain powered by its participants. In this engaging session, David, Aytunc, and Philip will explore how Mina can be a foundational tool for ZK proofs. They will introduce the feature of the Mina's o1js with examples, making it easier for you to build ZK-powered applications.
Moz?
Hey, Moz.
I think his connection is kind of lost.
Yeah.
Maybe I can share my screen.
Okay, let's start, David. Can you go ahead?
Yep. Slideshow. Okay, does this work? Yep. All right. before I start my short introduction and introduction about myself and Mina Foundation, I would like to first of all thank Akindo and Kinjo-san especially for helping us open this online global hackathon and also introduce Mina to the Japanese builders. Little bit intro about me. My name is David Park, and I'm the head of APAC at Mina Foundation. I actually joined this Mina Foundation early January this year. And one of the reasons why I joined was because Mina is the frontier of ZK technology. And we are in fact the only layer one that provides ZK programmability. That ZK, I believe, is a technology that would contribute to mass adoption of blockchain because it brings in privacy, data protection, at the same time verifiability, which I think is necessary for mass adoption for public ledgers. So today, I'll be giving short intro of Mina Foundation and Mina Protocol, and later on, we were able to invite Aytunc, one of our grantees of Mina Ecosystem Grant, Mina Community Grant. He's a very well experienced o1js developer, so he'll be able to give a intro of o1js, which is our ZK program language. And later, Philip Kant, who is our senior technical product manager and also a brilliant mind, would be giving an intro on our newly created fungible token standards on Mina blockchain. And Philip has been the lead in creating this fungible token standards. So he'll be giving a short intro and short overview of how to write the fungible tokens. So I'll just go on by giving a major updates. Before that, I would like to say I'd like to introduce Mina. So we were founded in 2017, and we were one of the very pioneers of ZK technology. And with using zero knowledge proofs for off-chain computation, combined with recursion, we were able to brand ourselves as the lightest blockchain, where with the 22 kilobyte with verifying one block, you can verify the whole state of the blockchain, which brings in more decentralization and trust to the ledger. And we launched with such design. We launched our mainnet 2021, and ever since then, we worked on programmability, where in such light blockchain design, where different kinds of ZK applications could be used, not only for off-chain and scalability use cases, but also for consumer aspects of zero-knowledge proofs. So last month, June 4th, after many arduous and persistent hard work and research, we were able to have our Berkeley upgrade, where we provide the ZK programmability. And the ZK program language is o1js, and it's a DSL of TypeScript. So it's a TypeScript framework where it is easy and accessible for developers to develop. And it abstracts a lot of the zero knowledge aspects, so it's easier for developers to build zero knowledge based applications. So after so one of the major news is we launched our Berkeley upgrade, and following up with that, one of the big use cases that we created was a partnership with Mirae, one of the largest investment banks in Asia to create a proof of concept on allowing the Mirae asset securities users to be able to create asset attestation through zero knowledge proofs on Mina. And this is all possible because of the Berkeley upgrade and easy development environment for o1js, which Aytunc and Philip will explain later. And lastly, we also, so since our upgrade, we have many ZKApps being launched right now. And there is another fun ZK app called Tilevile. It's a simple game, web-based game that is launched on Mina. So later on, when you have time, please search up Tilevile and please have a try because there are many campaigns that are going on right now. Moving on, I think Aytunc will be giving a short, giving a explanation on Mina and o1js. Aytunc,
yes.
you
Let
want
me
to
share my
share?
screen. Thank you.
Yeah.
Perfect. You can see, right?
Yep.
Awesome. So hello, everyone. I think David explained a lot for me, enough for me. I'm Aytunc, a grantee in community grants and a member of Navigator's exploration program. Today I will explain Mina and zero. Then we will dive into o1js, and I will show you an example application, recursive application that you can build with o1js, which is a provable Fibonacci sequence. First of all, let's move with what are zero knowledge proofs. Again, in a high level, zero knowledge proofs are some mathematical methods, proof methods that enables you to prove and verify information in a private, trustless, and decentralized way. What does that mean? Imagine you have some information that you want to prove someone. For example, a widely given example is that you want to get in to a bar, but security on the door wants you to show your ID to see whether you are over 18 or not. Okay, you can just show the ID card, but in that case, you just leak all your other information, sensitive information, and maybe you wouldn't want to do that. In that case, you could just, if you could just find a method that you would only prove that you are over 18, but don't show any sensitive information of you. Similarly, in computation methods, you maybe would want to save, preserve some of your information about your computation or about a statement. For example, the money in your wallet, vice versa, or even your public address in crypto space, which is done by, I believe, Zcash. In that case, you are able to use zero knowledge proofs. And for zero knowledge proofs, there are most of the properties of them, but especially in Mina, there are two properties that are that makes zero knowledge proofs very revolutionary. It says the proof can be checked efficiently, which is in constant time, and without exposing any of the private inputs. So what used in the zero knowledge proofs is, let me introduce some of them. You use some hash functions which are one-way functions that you give some input and it gives some output hash in string or number, and there's no way to convert this output to the input. And there are public key signatures where you have two keys, one public key and one private key. And using your private key, you sign your message and you come up with a signature. And then you use a verification function to verify that the message sent is from really your public key. And in zero knowledge proofs, you write some program, you compile it and get some verification key. And using this verification key, using some public and private inputs that you specify and this program, you create proof. And then you are able to verify this proof, which means that you verify that this program is executed or output is obtained in a manner that you said to the other people, as you say. You verify this with this proof public inputs, which was visible by everyone, and this verification key that you compiled from this program. Now, that was a zero knowledge part, and most of the Mina, actually all of the Mina, is based on this zero knowledge proofs. What are the advantages of zero knowledge apps is that since you are able to hide some private information inputs, you enable user privacy through the zero knowledge proof methods. And no guess, since your proofs are succinct. What succinct means is that you remember this first property that I said. Are able to verify a proof, which is a proof of a computation in a constant time. Because of that, you have a constant in a one time, which means there's no varying guess in that verification method. And you can make some composability and ZK rollup style scaling through recursion mechanism of Mina protocols o1js, which enables some tools that helps you to make it. And since Mina is a succinct blockchain, it is interoperable with other chains and ecosystems as well. Now, how Mina different is that other blockchains, since they keep all the transaction data or other transaction related data on their chains, and since there are so many transactions done every day, they include them onto the blockchain, and it gets bigger and bigger every day. Last time I checked, for example, Ethereum was about to get 1 terabyte or so, which is huge. And other chains are getting bigger and bigger as well. So in terms of getting bigger and bigger, and this eventually affects the new node operators to join to the network harder. But in Mina's chain, Mina blockchain's case, no matter how many transactions you done, no matter how many transactions you include to the chain, the size of the blockchain is fixed due to the recursive ZK snark technology, and it's 22 kilobytes. That's why Mina called a succinct blockchain, and this recursive ZK snark enable this succinctness. And what the proof system which enables this is called Kimchi, which is a setupless, efficient, and extensible proof system. Setupless means that there is no need for Okay, let's pass this part. This is not relevant to the workshop actually. So, oops, there's a problem. So let's give an example of decentralized applications and how do they work. In Ethereum, when you use a DApp, when you make some update on this DApp, it is sent to the Ethereum network, and every node it is executed, and the update is included to the chain. But in the Mina's case, you use the app, ZKApp, do your computation off chain, which is not done on the chain by all those nodes, but on your computer or on your server. Then you send some state updates and the proof that you done this computation correctly and validly. And with these state updates and proofs, chain is updated to the new state, and it is still 22 kilobytes. And how this happens is that in your transaction, you use some verification key of this ZKApp account, like smart contract accounts in other chains. And with this deployment, with this transaction, you are able to update the chain with this verification key. It is handled on the Mirae blockchain. If the transaction you sent and the proof actually you sent is valid, it is included to the chain, and it is not valid, meaning that your proof is false or doesn't reflect the correctness of the computation, it is rejected. And every ZK app, which your ZK app is simply a smart contract. You program it, and you write some methods on the smart contract, which eventually compiles to a program, which is some ZK circuit. What ZK circuit is a representation of some computation, let's say, which you can assign some private or public input, and in that manner you are able to give some let's say transcription that you say, hey, this is my contract, this is compiled to the circuit, and with this constraints in the circuit, this computation is done correctly. Let's move to the O1js and explain it in a better sense. O1js that is used for writing ZK apps. It can be used with other JavaScript. Perfect VS Code support. It is very easy. You can choose to use some ESLint, and for testing environment, just cryptography, and o1js and Mina as well is field element. To explain it well, I want you to think about the some analog clocks. The how they say Western type clocks, AM, PM, and so imagine it is 11 EM at the moment, and you look to the 4 hours later, let's say 9 AM. You look to the 4 hours later, and what becomes is this: 9, 10, 11, and when you get to 12, it is noon, 0, and then 1 again. What you do in this computation is that you divide any hour by 12, and if there is any any remainders, you use that number to talk about your time. Just like that, field elements are set of numbers. You can imagine a clock as some field that has 12 elements, and field elements in Mina, instead of as a clock taking 12 elements, can take up to 256 bits, which means 2 to the 256 elements. And if there are anyone who are familiar with Solidity, it is UN 200, similar to UN 256. And the field type is built in the o1js, where you normally would make some 1 plus 3 summation in some normal number number set. You just use field element field1 dot add and new field 3. Now you end up with a number 4, which is a field element of 256 byte field. And there are other types besides fields, like in ZKApps, this ZK circuits and provable programs, unsigned integers 32 and 64 bits, public key, private key, and signatures, which are backbones of modern cryptography, and groups, which is another mathematical structure, and scalar and Merkle tree structures. Let's check some example Hello World smart contract. Imagine you want a variable named X on the chain in the smart contract, and then you want to update it with its square. For example, you give X equals 3, and you want to update it to 9, and you say this to the using the smart contract. You say to the chain that, hey, I had 3, now I'm updating it with its square, which is 9. And then again you say, hey, the value of X was 9, now I'm updating it with 81. Is it correct? Yes, it's correct, chain will say, and verify it. But in this step, or second step, when you say, hey, I have 9 and square of it is 75, it will reject it because it is not the case, and it will not be the proof you create for this computation, so-called computation, will not be valid and will not be verified. Oops, it was supposed to be ZKApp. Let's not see this. Let's put this. ZKApps are written by classes, which you extend a smart contract class, and define a state, as we talked before. For example, X. You use a state decorator, which says that there will be a variable whose state will eventually be sent to the chain, and you will be able to check whether some statements you will say in the future about X will be true or not. And you can define the type of the state inside decorator, and it's not only supposed to be field. And as you remember, in the previous slides, we said that there are Boolean types or union types or group types. You can use them in state as well. And I think it's an old one. To initialize a contract, you use, even though it writes here, I think I forgot to change it. You can use init method, where you can initialize this smart contract code field class in your computer, where you can give some, for example, initial balance to the contract and set some variables, and it will be, the state of the contract will be changed in that manner. And when you want to send the state of the contract, this initialized state will be sent. And you can, as I said before, you can create some methods which are used to change the state of the contract in a provable way with method decorator. And when you do it async, which is in the recent update of o1js, I think async was the most used one, the necessity. When you use the update function method in this contract on these variables, you update some value. This in our case, it squares the field we chosen, as in the previous example, and you can assert equals to the squared value that you predicted. Then you can, if this expression is true, which means that the square of x is as you calculated by yourself, then the value of this variable x is changed as squared and sent to the chain by a proof. But there's one special thing I have to tell you about it. Now, this get expression does not directly get some value from the chain. Rather, it gets some value from your local machine. Then the local or development environment. Then all this code you write down is compiled to some proof, and then it is verified on the chain. It is not like other like Ethereum or Cosmos chains, that there are values on the chain that you can access and get. Rather, there are one small state which includes all previous data of the computation done. Then you, by your computation and proof of outcome, proof of that, you are able to verify your computation. Okay, we talked about it, and that's all we can say about smart. There are more to say actually, but some basics of smart contracts are, there are some state variables which are public, and you can initialize your function contract, and you have methods that you can give private arguments by default, and prove that the computation or you done or information you give is correct. By o1js, you can create some recursive computation thanks to ZK snarks, which is infinite recursion actually, and verify it on chain. Before diving this, let's start with, you can still see my screen, I guess. I would like to give some example use of Mina o1js by writing some, showing some Fibonacci sequence, which is a provable Fibonacci sequence. But before that, I would like to modules page, which is which explains the ZK Fibonacci, which we will I will show you, and it explains deeper and gives the reasoning of why to write Fibonacci sequences. So simply a Fibonacci, you add consecutive two numbers, get some output, and then add this output number with the previous one. For example, let's write here, you have 1 and 1 as start. You add 1 and 1 and get 2. Then you add 2 and 1, you get 3, and 3 and 2, 5, 5, and goes like that. Now, why would someone write a ZK Fibonacci? Maybe you would want to use some output of the 1406th step of Fibonacci sequence in your computation, a very serious computation, and your computer is not affording it. So in that case, you would maybe want to resort to one of your friends who has these supercomputers, but you have some trust issues. You don't trust him or her, and you want to be sure that the number you obtain from him is correct. Really, the 1406th Fibonacci number. To do this, you can use o1js, thankfully. To use it, to make some Fibonacci sequence with o1js, you start with creating some pair class, which is right from a provable struct that is given by o1js. You create first and second number, and you instantiate it with first and second numbers. Then you write some ZK program, which is simply writing a circuit. By circuit, what I mean is that you get some inputs, and there is some computation done here. Then you get some output, and all this done is verifiable because it yields some proof of the computation. What we do here is that in the ZK program, Fibonacci sequence ZK program, is we will have some base case which will have no private input yet, and the base case method is just returning you some the first two elements of ZK of Fibonacci sequence. Then you move to the next step with a proof that you completed the previous step correctly. Then in the step method, you take earlier proof as an input. Then you verify it in the first step of this method. Then you get the numbers of the previous step by earlier proof.public output, which are those two, if we think about the first second step. Then you return the new pair struct that the first one is the second element. Remember this. First one is now the second element, and the second one is the sum of 1 and 2, which is 3. In every step you do this. In every step you give some private input, the proof of previous step, and in every step you verify the previous step. In that way, you build some recursive program that that is known that in every step you are proving the previous one. So when you take another step, there is a chain going back to possibly infinity that is proven until the point you are. And when you write this recursive program, you compile it and get some Fibonacci sequence proof type, which is specifically for this Fibonacci sequence program. Then in the smart contract, you instantiate two variables, number 1 and number 2, you say, and those two variables will be on chain. You will be able to verify the changes, prove the changes of those numbers, and you initialize those numbers as 1. Then for updating those on the chain, you use some Fibonacci sequence proof. You verify this proof and state that the public output of the proof, which we obtained in this computation, and first of it is greater than the number 1 after the computation. Since our computation is getting bigger and bigger, this is a checking step. And once this assertion is true, you go to the next step and set the number 1 and number 2 as it is supposed to be. As it is, it would change in any Fibonacci sequence. So you write this contract. Now this is a ZK app, and when someone interacts with it and makes some computation and uses the update function, and if all these verification steps are done correctly, they will be able to change these numbers and send the proof and verification of this contract to the chain, and it will be verified, and number 1 and number 2 now on the chain will be changed. Of course, after all these steps, Mina blockchain will again stay in 22 kilobytes. You can think of how this 22 kilobytes work as this operation. You make some computation, then you return something that is again in the same size. Now, to test this application you start with, let's say, you start with defining some deploy and a ZK app address, which is like ZKApps private key and what ZKApp contract as we defined here. And before all, we will check if proofs enabled, which means that in the testing environment, you are simulating a Mina blockchain in your local machine, and then your computer is either making the computations for you and simulating the computations and verifications that would be done. Not computations, but verifications that would be done in the Mina blockchain. And if you enable proofs, it becomes more realistic. It creates all proofs, and as a result, testing would take longer, like 20 seconds. In this, the difference was around 20 seconds. Let's call it false right now. Now we will not enable proofs, so it will be a Mina blockchain simulation that makes verification faster. And you set active instance of Mina as this local blockchain. Then you get some deployer and sender account from test accounts of this instance simulated chain, and you define deployer and sender key as deployer and sender private keys as private keys. Then you create some private random private key for ZK private key, and then transform it to public. When you get the ZK address key, you create the ZK app of Fibonacci with an address of this. And also, you should be sure that this ZK private key is not leaked to anyone, because in that case they would be able to use this private key and update the ZK app, which would be changing those methods in a maybe malicious manner. Preparation phase, you can make some asynchronous local deploy function, which is simple, and execute some account update. When you want to, you are supposed to make it. By case, we found our deployer account for making this a state change to the chain, and we deployed this ZK app. Then, when we get this transaction, we prove it and sign it with the deployer's key. In that case, our key and private key of the ZK app, which will be computations done on this ZK app. Then, as a start, we will deploy the ZK app, and we will get the number 1 and number 2 states from the ZK app. And remember, we do not get this from chain, but from our environment that we are building. But anyone has this environment can make these computations, and anyone can use their own private inputs, private information for any kind of computation that you do. And if their computations or information are not true, then the chain will not verify it. It will be invalid, and you will be able to enable the changes to be done by any people who are making these computations correctly or have the correct confidential information. Now we get the numbers from the ZK app, and we will check initialize with. Then would eventually give us the 4th element of the sequence. Then we will start the base case, and we will have some proof of this base case. And again, we will check this number 1 and number 2 is 1. Then all in these 3 steps, we will execute the step method in Fibonacci sequence, which makes this computation, which is verifying a proof, getting the numbers, and returning the next sequence and next number pair for our Fibonacci sequence. We get the proof of this, then make this Fibonacci computation for our testing purposes. Then when we make all this computation, we are able to now update the ZK app with the provable Fibonacci sequence we've executed here. And since it will be true, it is going to be accepted by chain. Then we will prove and sign this transaction. Hence, we will update the values. Number 1 and number 2 values on the chain. Then we will get number 1.
Hey, Aytunc, we have a comment.
And
Can you please
number 2
more zoom? this script, for this script.
And check if it is correctly with our computation, our local computation that we did. Let's make it big. Yeah, I'm sorry.
Hi, Aytunc. Is it possible that you can to zoom in the script to for everyone to see well?
I'm so sorry about the now. We started this, uh, we made the proofs enabled for making the smaller time, but if you try it yourself and make it through, it will with a 20. We are now logging the, as we expected, second element of 40. Hey,
Hello.
hey, can you hear me?
Yes, I can hear you. Could
I'm
you
so sorry.
share screen?
At which point actually did I lose connection?
I think yeah, around
In the
here.
beginning, you say, and yes, okay. So what we did until here? Let's recap. If my connection is lost previously, we defined a pair struct for making easier computation in Fibonacci sequence. We created a ZK program, which enables us for a recursive provable computation. Then we created a smart contract, a ZKApp for Fibonacci sequence that we can store the states to numbers and which we can update by verifying the proofs. Then we built the test environment with defining deployer accounts, sender accounts, and ZKApp address and their private keys. We instantiated a Mina local blockchain, obtained the test accounts from those local chain, and created a ZK app with some getting some private key and run private key by using o1js private key class and getting a public key out of this private key, and then with this public key we instantiated again a Fibonacci ZKApp. Then we we got a local deploy function, which enables us to deploy an account and fund this account and make changes in this account with the account update class, and doing this within a transaction, doing the deployment transaction. Then we proved and signed this for making this changes verified on the chain and stay on the chain. Then we start updating numbers from ZKApp, number 1 and number 2, which is from our environment, but can be verified on chain that the numbers we get is really as it is. We get here. Then we 1 and 1, the initial case. Then we said we want to make 3 steps. We want to execute 3 steps of Fibonacci sequence, where we will start with a base case. So we will end up in the 4th element of the sequence. Then we will start 2 numbers to check whether the computation done in the ZK program is done correctly. So with those variables, we will make a normal local Fibonacci sequence computation, and then we will also execute it in the ZK program we have written before, and getting a proof of it. Then when we get those 2, when we get the function update method of the ZKApp, and since it checks if the proof is true, then the state changes occur. We give the proof of the Fibonacci sequence of ours. We prove the transaction with our key, with our private key. Then again, when all this update is done, we are getting the number 1 and number 2 state from the contract or in our local environment, and check whether they are consistent with the computation we done. And in case the test is not seen, oops. The changes will be logged in this loop. Since we made proofs enabled false, it will last less than as if it's true, or as if it is done on a real blockchain on mainnet. So as you see, the second, and I'm waiting for the 4th one. And I'm hoping that I haven't lost connection again. Right?
Yeah, we can hear you well.
Yeah, 4th element is again 3. Now, our expected values will be equal to 2, and this is how you. Yeah, it took longer than expected. So this is how you write a ZKApp, a smart contract, and verify some recursive program inside the smart contract, and by this method you are able to write any code, any program you make some computations and can verify on chain. By this method, now you are able to obtain 1406th element of Fibonacci sequence with no need to. You can think about any computation that can be done by provable steps, and you can verify them on some smart contract that everyone knows that smart contract that you are using, and you gave is really the output of the computation due to this update method or any update algorithm that you will write. Now it's a nice time to go back again. So there can be some steep learning curve building on Mina, and there can be some restrictions you may have encountered with. In that case, you can use ProtoKit, which is a product came out of the community, which is enabling you to build an L2, an app chain easily. With this app chain, you can create any application specific chain that you can specify for yourself. You can runtime. You can write some runtime modules, and this app chain is pretty modular actually. This you can write application logic of your app chain specifically for your own purposes. You can change the protocol to some level, which you are able to specify the block production of this app chain, or getting all the burden of transaction fees to yourself, or having some specified VM operations, and so. And also it comes with its own sequencer, which means that all these computations all this transaction sent will be sequenced, and then will be used for some block production and will be settled to L1. Also, I believe they are about to come up with some settlement contract where this settlement contract will enable you to communicate the app chain and Mina protocol more easily. So you will be able to have some sovereign app chain that can communicate with Mina using Mina as a settlement layer, and create your own specified chain that uses the ZK and privacy aspects of Mina. And writing your runtime module is different than writing some smart contract, but easier for any other non-blockchain or non-Web3 developer. What you do is simply, again, you define some states on this chain, and you are able to use some advanced types, which is not built in Mina, like state maps, where you can map some public key and some value. You can imagine it like some public key and the money or any quantity, like number of NFTs this key has, or vice versa. You can define it, and you can create unlimited on-chain state, where in Mina, I believe it is now restricted 8 states, but it will be increased in the next updates of o1js. And on-chain execution business logic can be written as this. Again, you can use provable types, you use provable type, and all these functions you write are in the end of the day transformed to a block proof. So again, all your computation is somehow transformed to a ZK, to a proof, and included to the Mina blockchain, which is pretty magical. So for the next steps, I would like to introduce you the Navigator program. As I shared the modules with you in the chat, I think they've shared in the YouTube comments. You can check Mina documents and various other Mina contents. Learn about Mina protocol, how to write o1js. You can reach to us through Discord and any other channels. And if you get an idea that uses Mina protocol ZK programmability, or utilizes Mina protocol, or you want to combine your product with blockchain, and specifically some privacy preserving technologies, you can come up with some proposal idea and submit it to the Navigator Scrum program. Then you can be granted, you can get some grant up to 30,000 Mina with some time duration of up to 3 months, and you can build your products better, privacy preserving products, or you can build your dream product. So that's all I'm supposed to say. But oops, sorry. I think this slide is missing here. I would want to share Dennis Bash. I will share his Twitter as well. He is the founder of Astromina, which is a weekly newsletter for Mina protocol. It shares the technical or business news about Mina protocol. So shout out to him, and my part is over, I guess.
Okay, thank you for explanation and a nice presentation. And maybe Phillips, you can go ahead for the next topic for the fungible token.
Sure. Hey, everybody. Can you hear me?
Yes, we can hear
Great.
you.
I had another slide on that slide deck. Can you share that again, just for the introduction to the topic?
I think Aytunc, maybe you can share the slide.
Yeah, wait a minute. Oops.
Right, exactly that one. Yeah.
Yep, I share mine. I took.
Yeah.
Don't worry
Okay,
about it.
thank
Yep.
you.
Cool, thanks. Right, so I'm going to talk about fungible tokens on Mina, which is a feature that is quite new and in fact currently in beta. So the Mina ledger itself does support custom tokens, meaning that in the ledger of the blockchain, you can hold not only Mina, but also tokens that you define by yourself by writing a smart contract that describes the rules for spending, for transferring, for minting those tokens. And we have been developing a standard for fungible tokens. And currently that is in beta stage, where we have an audit that is about to end this week. So the auditors have looked at it and have made recommendations, and right now we are reacting to those and implementing the recommendations. The idea is to have one standard contract that is ready to use so that people can define their own fungible tokens and deploy them. And then third parties like wallets or exchanges only need to interface with that contract. and then they can integrate with any fungible tokens that people have deployed. It does provide the common functionality like minting tokens, burning tokens, transferring tokens. And it has some customizability in the way in which you allow people to mint tokens by having a specific admin contract that is custom, that you can write your own or just use a standard one. It can also integrate with other smart contracts, meaning that other smart contracts can create account updates, which are like the basic building blocks of transactions. And other smart contracts can create account updates that move the tokens. And then the token contract itself can be fed these account updates and can approve them and make sure that like all the rules like satisfying total conservation of the token, of the number of tokens in existence and things like that are satisfied. And then basically say, okay, these account updates can be added to the ledger. If you want to learn more about that, the best way is looking at the repository. There's a link on the slides. And the repository contains the code and some documentation, some examples, and also the test suite is a good place to look at if you want to understand how they work. The main branch is called main, and since we are at the moment just reacting to the audit and are doing changes rapidly, today I will be looking at that branch that is indicated in the slides. And if you want to look at the progress of the audit, you can look at that board that's linked in the slides. I will now share my screen and show you the code in the editor. And we'll just have like a cursory browse of the code and the examples in order to give you a quick idea about like how things work. And then if you want to learn more, then you'll have a good like starting point and know where to look for more things. Right. Do you see my editor now?
Yes, we can see it.
Excellent. Okay. Right. So the first thing we'll look at is the file fungibletoken.ts, which is where the token contract itself is defined. It's called fungible token, and it extends this token contract v2, which is itself a smart contract defined in o1js itself, which is a bit more general than like the fungible token. It has a little bit of state in the contract, so that's what we saw earlier, these definitions of contract state. It has the number of decimals to a unit. It has a link to that admin contract that I mentioned earlier, which basically determines who can mint tokens. And then it also can be either paused or unpaused. There's also a feature in o1js called events, which is that any transaction that does certain things can basically signal those to the outside world by emitting these events. And it has events for setting the admin, for pausing, minting, burning, or for the balance change of specific accounts. There's a number of like administrative like things that you need to do. You need to deploy the contract, you need to initialize it. And then you have things like minting. So if you want to mint tokens, you need to specify the recipient where you want to mint those tokens and the amount. And then the contract will do that. It will check with the admin contract whether you are permissible to actually mint tokens, and then assert that that's the case. And yeah, then it'll mint the tokens and emit an event. It'll also update the special account that's tracking the total circulation of the token. Similarly, you can burn. That's something where you don't need permissions from the admin, but it's something that you can do with the tokens that you own. Then there's pause and resume. Another thing that users will commonly use is the transfer method. So you have one address that you get the tokens from. You have another one that you send it to and an amount. And then it'll just send those tokens if the tokens aren't paused at the moment. Another like important method is this approve base method, and there's certain variations of that. And that is, as I said, if you want to initiate token transfers from a smart contract, then the expressivity of transfer might not be enough. So you might want to like have certain conditions. You might to individually want to create updates to accounts. And what you can do then is that you create them in your smart contracts, and then you give that collection of account updates to this approve method. And then it will check things like the overall number of tokens doesn't increase or decrease in that exchange, and also check some other things that are important, like preventing flash minting and these kind of things, and then basically say that these account updates are approved by the token contract. And then there's informative things like get the balance of a certain address, get the number of circulating tokens, and then the events. And that's basically it. Let's also have a look at that admin contract. What it does is it has these four functions: can mint, can change the admin, can pause, and can resume. And all of those return a bool. And what they do in the standard version is basically they check whether you have provided a signature for a special administrative key, and if you have, then that's okay. So yeah, that's basically this ensure admin signature. It creates an account update that needs a signature from a special key that is held in the contract state. And if you have that, then all of these methods will return true. But if you want to have different rules, for example, one of the examples that we have in the test suite is that you have like a token where you have a faucet, and then anybody can just can create a number of tokens that is just limited in one go. And and then you would write your own admin contract, but you wouldn't need to change the token contract itself. And this not having to change the token contract itself is kind of important in Mina's execution model, which is an off-chain execution. So in Mina, when you execute a smart contract, you do the computation on your own machine, and you submit a proof to the system that you have done that correctly, which is to be contrasted to a system like Ethereum, where all the execution happens on the chain. The advantage of the off-chain computation, the advantages of the off-chain computation are that it's more efficient, so you don't need to redo the computation on every validating node. And also you can keep some of the inputs to your computation private. And that doesn't work, obviously, if the computation has to be done by the public validator nodes. The downside is that if you want to have an interaction between multiple smart contracts, then you need to have the code for all of these contracts in your environment. And so that is just a logistical effort and also a trust effort, because you need to execute that code on your machine. So you need to have a look at it, at least. The way that it works with the fungible tokens is that we provide that one contract that implements the fungible tokens. And then if you have like a wallet or something, you would integrate against that one contract, and you wouldn't need to integrate against like lots of custom contracts that people write. And because the user-facing functionality, like transferring tokens or getting information about the balance of a contract, because those do not need the admin contract, a wallet wouldn't need to get your custom wallet contract, your custom admin contract, and would still work. Right. The next thing I think to look at is the test suite. So we have a number of tests for that. And the tests check that you can deploy a token contract, They check that you can that you can transfer tokens. They check that you can't transfer tokens without providing a signature. They check that you can create transactions by creating the account updates individually and things like that. So let's look at the test file. Yeah, right. So this is like the total collection of tests. There are tests about deployment. There are tests about the admin contract in particular. So yeah, things like pausing and resuming and not minting tokens if the admin contract doesn't allow it. Then there are tests about the transfers. And yeah, and about interaction with other smart contracts, and also about like having custom admin contracts. So let's look a little bit about at the code. Deploying your token contract needs 3 steps. So you create a transaction. That's what's done here. So this await Mina transaction is how you create transactions in Mina. And you need to specify who will send that transaction, like a key pair for sending the transaction, the fee. And then in the second part here, this function actually tells you what the transaction does. In order to deploy your token contract, you will need to create 3 new accounts on the blockchain. So these need to be funded by this account update fund new account. You need 3 accounts because you need 1 for the admin contract, 1 for the token contract itself. And then we also keep track of the total amount of tokens currently in existence using a dedicated account. And we do that because it's a bit simpler than to keep it in the contract state itself. The reason why it's not straightforward to keep it in the contract state itself is that when you submit a proof for a transaction, the proof is always done against the state of the system at the beginning of the current block. And so if you have multiple updates to the state, or conflicting reads and writes, more generally, conflicting reads and writes to the state of a contract in different transactions, then you can't have those transactions be included in the same block. And the number of tokens in existence would be affected by multiple minting transactions, for example. And so if you want to have multiple transactions that mint tokens, then it would be kind of difficult to track the total amount of tokens in existence in the contract state. So we don't do that. There's also workarounds around that. So you have patterns like the actions and reducer pattern, but it's just simpler to use a dedicated account. So then you need to fund these 3 accounts. You need to deploy the admin contract. You need to deploy the token contract itself. The admin contract, during deployment, you specify that privileged key. When you deploy the token contract itself, you give the token a symbol and you provide a link to the source code. Those are like informative things. And then you need to initialize the contract. And initializing, you give it a link or like the public key to the admin contract. You say how many digits you want to have, like what the number of decimals is in each unit of the token, and you say whether you should be able to do transactions right away or whether the token contract should start in a paused state. And then you sign that transaction. You need to sign it by the deployer, so by the key pair that's sending the transaction and paying the fees. You need to sign it with the key of the token contract and of the admin contract. And then you create a proof for the transaction and send it. So that's how you deploy the actual token contract. Let's maybe look at how you send some funds as well, because that's something that's interesting. Or like, yeah, minting. Should mint for the sender account. So minting, again, needs you to create a transaction. And in that transaction, you need to call the mint method of the token contract. And if the contract that should hold the tokens doesn't exist yet, you also need to fund that new account. So creating a new account for a fungible token needs you to, you need to fund a new account with one Mina to do that. And then you sign it by the sender, so by the one paying the fees, and by the admin key. So by that, because the minting will call into the admin contract, and with the standard admin contract, you need to sign it with that special key. Yeah, and then you can send it, and then you can, in the test, we also we note down the number of tokens and the number of tokens in the account before the transaction, and then we check that we have more tokens afterwards, the appropriate number. Burning, and then we check that you can't mint without providing the signature. Let's look at transfers. So transferring from the token contract itself is quite straightforward. Again, you create a transaction and you call the transfer method. And the transfer method takes from public key, the to public key, and the amount. And so you provide those, and then it properly transfers tokens over from one account to the other. Yeah, it should not do that if you don't give a signature from the token sender. So that's what this await rejects does in the test. And then the other interesting thing is if you want to do something more than just sending from A to B, you can create individual account updates and then approve them by the token contract. So what we do here is we create one account update that takes tokens. So we say the balance from that. Oh, right. We need to update that one. It's deprecated. Yeah, and then we have an update for receiving the tokens to another contract, and then we just call approve account updates on the token contract on these account updates, and then and then they get that stamp of approval from the token contract. And they wouldn't get that if we took more tokens out of the of one account than we put into the other account, or the other way around. This one is a bit more subtle, flash minting. So that is if you were to put the tokens into an account before you took them out of another one, then you would, for a very short amount of time, you would actually create more tokens. And that's something that you shouldn't be able to do because, for example, you could think about those tokens giving you some voting power or something, and then you could have the voting account update in between those two, and then you would basically inflate your voting power. So we want to prevent that. That's something that the proof method in the fungible token contract specifically looks out for. Yeah, I think we could stop here, or we could look at how to write your own custom admin contract. I don't know, David, should we stop here, or should we talk some more?
I think this is enough.
Cool.
I think this is enough. Yeah.
Okay, yeah. If you want to know more, then basically looking at the contract itself, looking at the test suite, and there's also a couple of examples. If you look at the example directory, there are also examples how to interact with a live chain and not with a local mock. Yeah, well, that's that. Thanks.
All right. Thank you guys for the presentation. And by the way, sorry for the inconvenience earlier. I got bad connection, which caused the video to crash. However, thanks to the great Mina team, the session has continued smoothly. Thank you for leading the session, David, Aytunc, and Philip. These all inclusive explanations will definitely help all builders, especially how to build a Mina protocol using o1js plus fungible token. By the way, for the fungible token, we haven't released information, but the Mina team currently planning some new tracks. So later on, this information will be very valuable. So maybe like maybe you should check again later on. So, okay, now we have a live Q&A session, so anyone can ask the Mina team anything about Mina protocol. So feel free to comment on YouTube. So we got some question in the YouTube comment already, so let's jump in and see what you guys want to know. The question that we got is from Alaid Jamil. Thank you for the question. Can we have access to this documentation docs? Yes, sure. Like we will pass this document and basically slide on the Discord later on, so you guys can check whenever you want as well. So anything you guys have question, like you can put in the comment section. So for me, like I have the one question that I'm curious. So let's say I'm not personally I'm really like kind of beginner builders. So maybe I just can code like TypeScript or JavaScript, but like really like beginner level. So for those who hasn't built on the Mina protocol, but who can code like TypeScript or JavaScript. So for those, yeah, for those who with this kind of knowledge, from what should they start and what should they refer to for the beginning? If you guys know the references, or yeah, it will be helpful.
Yeah, one good reference to that is the docs.minaprotocol.com. There's a number of tutorials where there is code that you can check out from GitHub and then go through the code, deploy it on the chain, interact with it. I think those are pretty good place to start.
I see. And as well, of course, like today's session will be very helpful.
Yeah, that
Yeah.
too.
And how about like ProtoKit? Like is as well like for the tutorial for ProtoKit is included in the documentation of the Mina protocol?
So if you search up protokit.dev,
Mhm.
there's a site where they have the they have the documentation and pseudocodes as well for reference.
Okay, great. I think I will post that information as well in the Discord later on, so everyone can check the details of with what they want to build as well.
And I
And
also want to add that if you have any specific questions, usually you can ask those hands-on questions to Mina community on Discord. So please search up Mina Discord and join in the channel and ask any questions if you have. Same with ProtoKit.
awesome. Yeah, everyone can join Mina Discord, and they can ask whatever they want there. So I think let me double
Sorry,
check
Moz.
if
Yeah, we have last question.
yes, we have. Okay, thank you, Lam Kai. Uh, is the source code for the question is the source code for the last presented open source? If yes, could you please share the link? It's basically for the fungible token code, I guess.
Yeah,
Uh,
yeah,
Phil- yeah, Philip,
yeah.
could you
That's
share
open
link?
source. Link from the slide. I can also just paste it into the chat if that's more helpful.
Yeah, I think I will post later on all of information in the Discord, and you guys can check detail of it. Thank you for that. Thank you for the question. So if you guys have any other question that maybe seems like that's all. So, okay, so I think the question will be, oh, by the way, don't worry if you missed some parts of this online session. This session is being recorded and will be published immediately after the live stream, so everyone can watch again. So, okay, I think that's all the question we had for today. Okay, all right, we are nearing the end of the online workshop today. So before we wrap up, David and Aytunc and Philip, do you have any message you would like to leave to the builders and potential WaveHack Global submitters? So maybe let's start from David.
Yes, on a last note, as Mose mentioned, and thanks to the wonderful and simple explanation of Philip, we are going to launch a new hackathon track with regards to Mina fungible token, and um, it will it will be a simpler set of work to do because we already have the standard made. So we would like a lot more developers to get hands-on experience with o1js and be involved with Mina ecosystem. That's it for me. Atuk or Philip, it would be nice if you guys could also share some of the last comments.
Sure. I mean, one thing is maybe about like setting expectations when you start coding with o1js on Mina. It is a different execution model and a different programming model than you might be expecting from coming from other blockchain systems. I think it's really the way to go, off-chain execution, just for those two like very strong reasons. Like it's much more efficient, and you can have privacy in your code, and you don't have to reveal all your inputs to your computation if you do it yourself. It does mean, however, that like a lot of the things that you might just be used from working on other systems like Ethereum, just need to work a bit differently. So have some patience, have some curiosity, and be open to like a new experience. And if there's any roadblocks that you think you're hitting, then yeah, ask questions on Discord and like tell us what you're missing. We are like, yeah, we will be working to improving your experience working on the blockchain. But it's a new model, and with all the pros and cons of that.
Yeah, right. And I think maybe if you
Yeah,
Philip.
agreeing with Davis and Philip's words, I would like to add that um, our documents are increasing. The information produced in community is mostly focused on Discord, but we are trying to get it out from Discord to web pages. So people can reach us through Discord or any other channels like Telegram or real life. So, and when they have an idea, they are encouraged to reach us, and we will provide the documents and help building and designing the application. That's all I can say.
All right. Thank you for encouraging builders. It was fantastic session today. Big thank you to everyone for your active participation, and special thanks to David, Aytunc, and Phillips for sharing such an insightful knowledge and for answering all questions. It was truly valuable learning experience for everyone. So as we wrap up, let's keep momentum ongoing. Mina's build theme at WaveHack Global is build applications with ZK proof using o1js or ProtoKit framework. And plus, maybe later on, you guys will see the new track as well. This theme challenges you to offer practical utility using Mina's zero knowledge proofs for consumer ZKApps. Zero knowledge proofs offer both privacy and verifiability on chain. So get creative in exploring value creation. As you can see, the grants are currently carried over, and $4,000 is ready to be distributed for this wave. It's a great opportunity to contribute to the Mina ecosystem, showcase your technical skills, and present innovative ideas. Be aware that it's very important to use o1js because it's or like protokit because it's a crucial criteria for this program. Probably the easiest way to use o1js is using protokit. Also, don't forget this WaveHack Global program is not only a chance to win a grant, but also an opportunity to contribute to a growing Mina community. So for ongoing resources and support as you build your projects, keep an eye on the Luma page and stay tuned for upcoming session. In fact, we will hold 2 events in a row tomorrow. One is with the Japan DAO Association, and the other one is an AMA with Mina Protocol on X. So stay tuned and don't miss this opportunity to catch up on Mina Protocol. We are here to help, and if you have any questions or need further guidance, don't hesitate to reach out through our official channels such as X and Discord, plus Mina official channel, X and Discord. So plus Mina currently has a survey regarding this online workshop. So please complete the survey and let us know how the workshop was. And you can complete the survey through the link in the comments section in the YouTube, on the YouTube. The URL is explorepunkpoll.com. So, all right. That's all for today. So thank you once again for joining us today. We look forward to seeing you at our next session and can't wait to see what you build. Okay, guys, thank you guys for today and have a great day, everyone. Let's keep up building.
Thanks, everyone.
Thanks. Bye.
Okay, thank you. Yeah, now, close YouTube Live. Thank you for guys.